No, the video.
Share screen.
Oh, I can share screen. All right. All right. Does anyone?
Yes, on students.
We are zooming right now.
Quite timely with third England PRL coming out.
Can anyone on Zoom confirm that you can hear me and see my screen and stuff?
Want me to go?
Is that
That's a yes.
is that a yes? Put a hand up or
If you overlap the whole thing, you should be able to see the mic.
how do I get the
The
menu back? This is the menu. I hit it.
there we go.
Oh yeah, okay. So I'll take that Karina as you can all hear me. So thank you. All right, should we get started? Okay, this is, well, thanks for coming to the Journal Club. This is I think a milestone paper in the kind of stuff that we're doing. Two-photon inference from a quantum emitter in hexagonal boron nitride. I think this was word for word the title that we were all wanting to have our names to, and they took it. They did it first and better and easier and quicker than we did. So good on them. Well, it hasn't been published yet, so this is still in the archive. So for the benefit of the group, I'll sort of go through a number of sort of the key concepts, and I'll maybe prompt some engagement from the audience, and then also ask non-rhetorical questions that I don't know the answer to, and hopefully we can all come away with a little bit more knowledge of this. So to begin with, we can consider the sort of brief bit of papers that have come out on this platform in HBN. A lot of other solid state platforms have already achieved two-photon interference, and in HBN this has been the first one, and there's only been sort of half a dozen papers over the last couple of years. The first couple were just looking at basic PL of these blue emitters under kind of experimental creation conditions. On the right are all the kind of parameters I can find in papers for the different electron accelerating voltages and also the currents. And what is interesting, I think, is that the method that Fournier and friends use is relatively high energy and pretty decent size current as well, and also very large radiation time. The ones that Ivan and I used for our papers here were relatively short, I think, from what I could gather, radiation times, and then Angus's original paper used a range of times, but it seems like this team sort of stuck with this method for this paper.
So Jake, I guess they're using also not the focus beam there, right? Those might not come through.
Yeah, that's a good point. I did read briefly in this one, they go into more detail, and then this one they kind of just reference back to this paper. They do note the beam diameter. I can't recall what it was.
Yeah, I think it's gonna be the fluids, the current density is probably the more meaningful term than just a non-area directed current.
Well, there's actually more to it than that, like the flight thickness matters. And then these energies translate to different energy densities. Because the lower the energy, the smaller the volume in which it's dissipated.
Right.
And that volume shrinks way faster than linear wave of energy. So say if you go from 15 keV to 5, it's a factor of 3 reduction in energy, but the volume you dump it into is reduced by like an order of magnitude or something.
Right. Yeah. Makes sense. Yeah, they I do recall they mentioned in this one they had also particularly thin flakes. So there are some maybe limited inferences we can make from these comparisons.
Can you guys hear me? Sorry to butt in.
Yes. Yes.
Just for a clarity, like 2 to 6, they all should be nanoamps, and in 2 and 6 as well. The way they do it is, yeah, they do a defocus beam, but they effectively make like a very high sort of or relatively high density sort of number in the center, and an ensemble in the center, and then they often actually pick the ones outside, like the singles that kind of, you know, that are sort of either from backscattered or stray or something like that. So they don't necessarily choose the ones in the center. Like we were trying to sort of create one, they create just a whole bunch and then grab the ones on the side that are kind of isolated. But anyway, there's just some clarity there.
Yeah, that's the point. All right. So that's the kind of small bit of the literature that is on this particular emitter. And in the broader context, just to maybe position this sort of result in the field, considering the different platforms that can do two-photon interference. I was kind of thinking of what you can kind of have in the back of your mind as the point of all this. And this is a good paper from Vayner and friends about the quantum internet, which is a very kind of hypey phrase and idea. But one of the things that I found interesting in this paper was this first paragraph, where they compare the potential of quantum communication to things like quantum computation. In the latter sense, or in the latter technology, classical computers can simulate quantum computers up to something like 50 qubits, and that's logical qubits, not physical qubits. And so there's a kind of the point at which quantum computers need to be better is actually quite high, whereas because quantum communication relies on this aspect of entanglement, which has no classical equivalent, the difference or the divergence from classical communication is actually quite early. Down here is a snapshot of the presentation by this company called Connect, which is a US firm, and they're interested in this idea of distributed entanglement. So the basic idea is you have some kind of source which produces pairs of photons that are entangled, and then they'll have some kind of distance through which they can be thrown into fibers. And you can actually extend that distance by having this outer module, which does this swapping operation. And then now you have entanglement resource, which is over a larger distance. And in principle, you can keep doing this. Then you have this network of entanglement. And then here are some potential uses for these things. But I think maybe the full potential is sort of something that we can't really fully comprehend at this point. This is a brand new kind of technological resource, which I think is pretty exciting. Also in this paper, they mentioned that a lot of these solid state spin photon interfaces platforms have already been achieving this stuff, and now HPN is in this sort of group of materials. This is a pretty good video if you want to get more information on this kind of idea. Okay, so it's just kind of something to have in the back of your mind. So in terms of getting to the point where you can do two-photon interference, we kind of need 2 photons to begin with, and there are a few ways to do this in the kind of platforms that we're looking at in this group, in this field. So on the one hand, you can have a single photon emitter, which just shoots out its single photons, and then you can have this kind of interferometer setup. Does anyone know what this one is called? This kind of setup? Have a guess? It's the Mach Zehnder-ish interferometer. So the idea is you have some kind of beam splitter cube or fiber-based beam splitter that takes one path and puts it in 2, and then on this, one of the paths is just longer than the other path. And if you're using continuous excitation of your emitter, the length of this path can be benchmarked on or baselined on the lifetime of your emitter. And if you're using pulse, then you can just use the equivalent length in take the pulse duration and sort of convert it to a length. And that's this length. And then so what happens here is you have successive, yeah, repetition. Yes, not the pulse duration, but the repetition. Yeah. What happens here is you have consecutive photons that coalesce, or they meet at the beam splitter, and then you have detectors afterwards. A different way to do it is to just have 2 single photon emitters, and then you don't need this whole stuff here. You just have them both into a beam splitter, and then you measure these 2 detectors. Is anyone else aware of any other ways to obtain 2 photons for experiments like 2-photon interference?
How about n photon interference?
N photon interference?
Because in that case, you can expand your spike. Normally, you talk about cubic, right? The 2. So your beam splitter only 2 points. So think about your beam splitter are n point, and your vector spike now n. So in that case, you expand your spike to n power n.
How would you get N photons?
For example, normally we do the so your basic vector is normally we're talking about the horizontal and vertical variation, right? Our base is normally horizontal or vertical.
Yeah, that's one
Yeah,
basis. I
yes,
guess.
so if we extend to the OM, because we have much more basic OM, because for OM we have -2, -1, 0, 1, 2, right? In this case, we expand, you can do
Yeah, so Tin was saying, just for the people on Zoom, if you have degrees of freedom of photon freedom which have more than 2 variables, then you can in principle interfere more photons at this kind of meeting point than 2. I think there are sort of multi-photon emission events which might in principle also be a source of these kind of photons.
Hey, Jake, in the delay line case, what's the actual, like, is there any definition for the requirement for the 2 photons arriving at the beam splitter? Like, let's say it's continuous wave laser.
Yep.
You know, say a photon, like one comes, and another one comes half up another second later, and that could be 10 nanoseconds later. Is that still fine? So the delay line is set for, let's say 3. Let's say the average excited state lifetime is 3 nanoseconds.
Mm-hmm.
So does that mean you're actually losing a lot of them because they won't interfere? Like, at which point are they no longer simultaneously? Like, what's the definition of simultaneous for the arrival of the beam splitter?
I think we can use these images to discuss that. So my understanding of what fully constructive or destructive interference would require is this degree to which the wave packets or wave functions overlap. And you can quantify this using something like an inner product of the wave functions. So you just take the two of them, you multiply them together, and you integrate. So so obviously in this picture, our sort of photon wave packets have a distribution in time and then also space if you're looking at the space domain. So there's a region over which the sort of value of the field is non-zero, and it's not the case that you would need to have them exactly on top of each other to get this effect. My understanding is that you would need to have some non-zero overlap of the two wave packets when they meet at let's say the beam splitter, for there to be a probability of this kind of
So
bunching waves.
what is the duration, time, like what is the wave factor, like you have enough time, arbitrary units here that actually have units on a, do you have a feeling for what that would that be like nanosecond or 10 gigaseconds?
That's the lifetime of your like this wave packet. It's a completely coherent wave packet. That your wave packet extends over the entire lifetime. That's my understanding.
Yeah, so my thinking is that the range is just, it is the range of the photon wave packet.
I guess if you start with the ideal case, lifetime limited photons, you've got this like energy time uncertainty, which literally turns into your like coherent oscillation, which is essentially what that is meant to represent on the left. And so if you have like a 1 nanosecond lifetime emitter, that means your oscillation decays sort of exponentially over one nanosecond. And in the frequency domain, it'll look more like a pulse, like that is.
Does that really make sense? Like if you extrapolate the idea to process, let's say your lifetime is now, second, or what? Like a pulse time. Some lifetimes can be very long. Or in a less extreme case, let's say that lifetime is in the millisecond range.
What is the frequency distribution of those things? Narrow?
What you're saying would imply that it's.
Well, if they are, then what I'm saying still makes sense.
Can you reword the question?
Can I reword it?
What's the main concern?
Well, the main question was what I was really thinking. So if you go back to slide 4, are you actually losing some fraction of the photons in the the consecutive ones are not arriving at the beam splitter simultaneously?
Yeah, Miloš, you will, but it's kind of irrelevant. Like it's not something that is quantifiable. So.
Well, is it not quantifiable, or do we just not know?
Well, if they don't arrive simultaneously, where simultaneously is some kind of has some uncertainty, right? Some duration of time over which you would consider them to arrive at the same time.
Jake's cartoon in the next slide is accurate, but so just don't overthink it. That just schematically it is what it is.
If they arrive differently, then they're not going to interfere. It's not going to get this effect.
Ritika, Miloš was asking like if we lose some photons because they arrive either a little bit different spatially or spectrally, or and the answer is yes, you would lose them, but there's no way to quantify it because you just flow photons every nanosecond or so.
There must be a way to quantify it. So we just don't know, right? I mean, like what I'm saying is there's a distribution of delta T's in between the photons being emitted. And even if your average lifetime is some number, let's say it's 3 nanoseconds, for any 2 photons, consecutive photons, that's going to be fluctuation, right? It could be 0.1 nanoseconds, then it can be 9 nanoseconds, it can be 3. can be 15.
I don't think that's so. I think that's a particle interpretation, and for this to make sense, you would need a wave interpretation. So it's not the case that
It's a wave pocket, but it's not really a wave pocket until it collapses at the finish, right?
it doesn't collapse.
But sure, it doesn't matter as long as the delay line is longer than of the lifetime of the material. And it doesn't actually matter if it's better if it's like you make it multiple than a lifetime, but it still doesn't matter because if you have any dephasing events or anything like that that causes some future in your spontaneous like emission, and all that matters is the wave packets are identical. And then if you measure the interference with respect to time for different wave packets when they collapse, that zero delay time is what you quantify your like level of interference as. I guess we get to it in the slides.
Yeah, well, I don't know, because then what you're saying is that the delay line can't be too long. It's impossible to be too long. Right? So
Well, Milos, the delay line is
what if the delay line ends up being 2 minutes?
It's fine.
Can be 2 minutes. Fine, will still work.
Can be, why not?
Milos, it doesn't matter. You can have a delay line of a kilometer as long as you don't have absorption there. It's fine.
And there's no spectrum.
It can be short, but you
still interference, right?
Okay.
Yeah, you do self-interference if it's shorter. It can be shorter, but you don't do 2 photon. You do 1 photon interference if it's shorter.
Yeah, Jake, move on.
Yeah. Okay, we're already 25 minutes in. Okay, so for this experiment, we want indistinguishable photons. So now we have this idea of what is the difference between distinguishable and indistinguishable. On the left there, I've tried to illustrate this, that indistinguishable photons have the same sort of value for all the degrees of freedom of the photon that you can think of. Some of the ways that this can be changed are on the right. So the top right is something like what you would get if you have 2 photon wave packets of different energy. What type of phenomenon can lead to this result is a question for the audience. Oh, we have chat. Should I be looking at this?
Jake, I didn't get the question, but move on.
Okay, so
There we go.
What's the question?
So
You're saying to move on without even knowing what the question is.
okay, so here's an example of what you might see if your system is subject to something like spectral diffusion, which gives rise to different energies.
We just answered your question there.
Now here's so that's what I was looking for. Now here's another opportunity for the audience to engage in this. In this one down here, I've illustrated, attempted to illustrate what happens when you have a kind of instantaneous dephasing event, where sort of the left half of the wave packets are indistinguishable, and then the right half are not because of this discontinuity in the phase. What type of phenomenon can give rise to this result, do you think?
Polarization.
What, polarization? Not quite. Igor, what do you think?
Well, I'm not sure. I mean, you wrote phase, so I'm not sure what answer are you looking for.
So this is
What causes the thing in the right hand side? Take it on the bottom.
what would cause this kind of
Well, it's your either polarization or your phonon broadening. So one of the two.
yeah. So this is my attempt to illustrate phonon interactions, dephasing.
So, but anyway, because it is spontaneous emission, right? So that means you always have some kind of randomness in the phase. spontaneous emission, even with the isolation, atom, we still have the phase randomness of the phase.
That's within the lifetime, right?
Yeah,
That's the limitation of the lifetime.
No, I mean, the phase, the randomness of the phase, we never have the full wave packet like this for every photon. Because every photon which will different from the real photon.
I think,
Even this
when you
point.
think about that, for spontaneous emission, all it, you can, where I interpreted it as like the mean position of the envelope in time has changed.
Yeah, the phase also.
Well, relative to like some absolute, like continuous wave, yes, but actually that again doesn't matter. If you imagine just, if you imagine just a wave packet, it can be exactly the same, but at a different.
The wave packet is never the same. It's better than was
Spontaneous emission, it can be exactly the same.
No, it cannot be.
Okay.
It cannot be. That's the reason why we need a cutting.
We might revisit this idea of dephasing in a little bit, but the other question I posed here is what else can we use to tell photons apart, which is the thing that they used in this experiment. What does anyone think? Anyone got any ideas of other degrees of freedom of photons?
Say again.
How else can you tell two photons apart? How else can you distinguish two photons? How did they do it in this paper that we're talking about?
G2.
Not G2.
It's standard HOM measurement, isn't it?
So they changed the polarization. Polarization is another degree of freedom. I didn't bother doing that here because you need like 3 axes on it, and I was like, this is good enough. So polarization is another way you can distinguish photons. Okay, moving on. What's the deal with two-photon interference? How does this all come about? You may recall this paper that I talked about early in the year when we looked at another two-photon interference paper. It's pretty good. The intro section has a really good sort of accessible introduction to the theory of this. And then the rest of the paper is basically applications, which is also worth reading, but I haven't really looked deeply into it. In this image, you'll see something that should be, I think, pretty intuitive about what we'd expect when we have photons that can go into a beam splitter from 2 directions, A and B, and it can exit also in 2 directions from C and D. So when you have a photon in each input, there's 4 possible sort of outcomes that you would expect. There's 2 ways for them to exit the both on the same path, and then there's 2 ways for them to exit on different paths. And the way that you write that mathematically is like this. You just hit the vacuum field with these gradation operators, and then you sort of do all this algebra and you get these 4 possible results where this notation means that, for example, in this possibility here, we're creating a horizontal and a vertical polarized photon along the C path, and likewise for the other ones. This negative sign here ends up being important for the indistinguishable case, and you'll recall from the previous journal club that this exists because of arguments to do with conservation of energy and the way that that beam splitter works. So now we consider the case where instead of having a horizontally polarized photon along this path and a vertically polarized one on this path, they have the same polarization. In fact, the same of all the degrees of freedom of photon. Let's say they're both horizontally polarized. And then we could assume that all the subscripts are H's and don't bother writing them. So you do the same thing and churn through the algebra, and you get that these 2 possibilities destructively interfere. And what you're left with is this case where either there are 2 photons in, no, not either. It's the case that the state is in some wordings, a superposition of having 2 photons in this one and 2 photons in this one, such that if you were to measure the output on this one, it would determine the output on the other one.
So that means that the curve of the 2 are the same time.
Pardon?
The curve are the same time.
Same time.
Yeah, that's the final one.
Yeah, so this is
Why you observe the
a kind of basic analysis where we assume that there's no temporal variation.
So, but that means that if you observe that with the correlator, that means you observe the coincident event at the same time, rather than they're not coincident at the same time. That's what better is for your interference.
So in these cases here, you would observe coincidence events. If you put a detector here and a detector here, you have one photon on this path and one photon on this path. They don't know about each other.
Yes, I know, but that means that you cannot observe the diff. Because it's the same time. So that means you only have the angles at the same time, right?
No, when you measure it and you break the entanglement, and you know that you don't know.
There are some description they're not correct because there should be either way you have the B or D, or no CC or D, either way or C or D, but then the same time.
I don't understand the question or comment.
I'm not sure what Tin is saying. What Tin? It's all correct here. That's physics.
Igor said it's physics. Let's maybe subsequent slides will address some of the questions.
Wait, Jake, can you go back one slide? Actually, one thing is important here is what's the origin of the sinuses, of the minuses.
The origin of the sign
of the minus.
Yeah. What do people think about that? Yeah, I did mention it. Did everyone catch it?
Is it clear to everybody why there is a minus there?
Yeah, so this whole thing works because of, I mean, it's reflected in as working in the algebra because of the sign difference.
Why the vacuum there? Zero in the vacuum.
Vacuum.
Yeah, the zero in vacuum.
Why
Yeah,
is
that's the signal from why two signal from why?
this is the
Zero.
three standard notation.
The zero means zero means the vacuum. Vacuum, but why the vacuum state there should be state one, right?
Well, this is that you get a photon state and you give it to duration. This is the same notation as a one ket. Except you do it this way because then you can use standard out. That's a
And also you have two-photon. You have two-photon. Let me check the mathematics data is quite different.
Yeah, you can review this paper and tell me what you think. So the sign difference comes from this conservation of energy, and another way to think about it is the fact that to actually achieve this in real life, you need a kind of mirror thing, and there's a difference between the two paths. One of them goes through this kind of the extension of the mirror picks up this phase difference, and then that is manifest as a negative sign. That's right, right? All right, moving on. Mostly when we're doing single photon experiments, or we're interrogating our single photon emitters, we care about the version of G2 plot, which has the dip that goes all the way to 0 at 0 time delay. But in this context, there's the difference between that and the case for two photons is significant. Down the bottom here is the kind of general formula for what these curves look like when there's no sort of noises or extraneous sources. This notation is the expectation value of the Umbra operator operating on your photonic field or your photonic state. So basically the dip increases according to the number of the photon number state that is incident on your beam splitter in your standard HBT setup. So when you have single photon states, the dip goes all the way to 0. When you have two photon states, the dip goes all the way to 0.5, and all the way up to the case where you have basically arbitrarily many photon states, and you get the flat line. in the context of these experiments, what we end up seeing is something like for indistinguishable photons, you don't have these coincident events. And so you basically get something that looks like the case where you only have one photon states. And for distinguishable ones, you have these two, you get two photon states. And so this is kind of the signal you look for is if you can change your setup so that you change the photons from being indistinguishable to being distinguishable, then you should see your result change from this blue line to the orange line. That's the goal. Okay, so here are some kind of leveraging that sort of concept. Here are some things you might look for if you're doing this experiment. On the left is for the continuous excitation case, where you have the setting for your, you can make it such that your photons have parallel polarization if you're using polarization as your distinguishability criteria. And then you see the dip look like what you get for a single photon state. And then you can change them to having perpendicular polarization, and then you see the dip look like what you get for the two photon case.
So you, to clarify this measurement,
yep.
If you had a delay line, which was just completely wrong for the lifetime of your system, you could still get a nice G2 from a single photon source, but the change in the polarization along one of the arms wouldn't yield any change in this G2 measurement for you. So that's how you distinguish between those two scenarios.
So if you have the delay line, which is less than the line,
yeah, for the system you're looking at,
and you still have the ability to go from polarized parallel to perpendicular polarization.
Yeah.
Then
I think that's why it's quite a clever measurement that Joanna set up on the manual.
yeah, it would still, your intuition is it would still yield the same.
You could go from the parallel to the orthogonal polarization state, that G2 curve would be equivalent.
Yeah, so it's like robust.
Yeah,
in that sense.
Equivalent to one, like I'm having equivalent to that picture. Or equivalent
so
to
the red boron curve there, if you change to the orthogonal polarization state, you'd still have that G2 not tau 0 would be 0.03. The green curve would exactly overlap. From my understanding, that's why it's quite a clever experimental setup.
Wait, John, what, Jake, what is John asking?
So assuming you have a perfect setup, you would expect this result. But if your setup is imperfect in the sense that the delay line is not the right length for your lifetime, would you get only the bottom curve for both settings of the polarization?
No, you would always get one less, one more. If your delay line is imperfect, the bottom curve with the two parallel photons will never go down. It will just be almost identical to two photons.
My feeling is you would still be able to discriminate the two.
Yeah, you will be, but the discrimination would be much worse. This is nearly perfect. If you fuck up your if you screw up your delay line, then the brown or whatever purple curve is not going to go down that much.
Yeah, so I guess in the word we should be using is the visibility would deteriorate.
Yeah, correct.
And so one way to quantify the visibility is to look at the relative difference or the ratio of the difference in this between the dip for each state and then the dip divided by the dip at this one. So obviously, if this goes all the way to 0, then your visibility is unity. And if it's very poor, then you get a visibility close to 0. In the pulse regime, there's a few ways that I've seen visibility quantified. One way is to do the same thing. You just consider the value at 0. But it kind of misses out on this interesting aspect of the pulse regime where we see the decay of the pulse is, in a sense, based on the excited state lifetime of the emitter. And the dip that you get for zero delay is related to the coherence time. And you'll recall Twan's favorite equation here, the coherence time is dependent on the excited state lifetime, and the pure dephasing time is also some spectral diffusion rate. So the idea is that if you sort of have no spectral diffusion and your pure dephasing rate is sort of infinitely long, then you get this limiting case where the coherence time is twice the excited state lifetime. And in that case, the area of this region would be 0, and that's perfect visibility. One attempt to quantify visibility in the pulse regime is to take the area of one of these pulses corresponding to non-correlation events, which is what the way these authors describe it, at a time that's not zero delay time, and then find the difference between that and this area here, and then divide by sort of this area. This is similar to what is done with in this paper by Fournier and friends. Okay, so the point of this page here is that at the end, you do this experiment, you want to quote a single value, just like we quote purity for G2, regular G2 experiments. Here, you want to quote visibility. You want that number to be high. So for this experiment, we want indistinguishable photons, and the photons we get out of our single photon emitter, some of them are sort of high quality and good for this experiment, and others are not, by virtue of the fact that they have been produced in concert with this kind of interaction with the lattice, which produces phonons. So this image here is a off-resonant PL spectrum that I took for the first Blues paper, and I looked at the data and decided that obviously there's a ZVL here, and then there's a few other bumps. And just reading around, it seems like these, given by the sort of difference between bumps and the ZVL in terms of energy, these are often labeled as longitudinal acoustic phonon modes and also longitudinal optical phonon modes.
So Jake, can I just ask, this is your data, right?
This is my data, yes.
So did we, and I guess you have a G2 from this, but did we ever confirm that this, what you label as LA1, is actually not ZPL2?
We did not, but it is also mentioned in the Fournier first paper. They have a similar
Yeah, but they also didn't confirm.
yeah, that's true. So
Well,
we're wrong and they're wrong too, I guess.
but yeah, so I'm not convinced actually, because of this Christoph Becker analysis. So that he reckons there is no LA1 basically. He reckons all the emissions is always 2 ZPLs, and so actually lack of good visibility. Well, I mean, it's hard to disprove or prove, but I mean, it's something to think about, I guess.
Does that change anything, Igor?
It does in a way, because if you're doing now, if you're doing resonant excitation, visibility should be basically 100% almost. But if you're doing off resonant, then it's going to be basically shit. And also, if it's the second ZPL, then the emission should be in principle much more coherent than if it's a phonon side, because it's a phonon side, then it's incoherent. So actually, the fact that they, yeah, I would stop here. So it doesn't make any difference in principle now, but it will make difference as we move ahead.
Well, no, you're the second CPL will have quite a different lifetime from the first CPL, right? So it's not necessarily that it's going to be more coherent than it's a one cycle.
Well, it's going to be more coherent if you excite on resonant and you don't touch that other ZPL. Then you're really only working with a super high Hoang-Gris factor, like a super high, like a super high ZPL to phonon sideband ratio.
Yeah, I agree. There could be some differences in your home tip. I agree with that.
But then
Some of the other stuff you said I don't agree with, but we can go into it later.
And so the other thing is that these guys in France, they don't see this hump, right?
The they don't see the acoustic
They
mode.
don't see LA1, right? They only kind of see the ZPL.
Well, that's what this is.
But what's inset? The inset is very, it's like the inset is,
Maybe after the filter or something.
But in the medium and they filter it anyway, they filter the CPL.
anyway, just bear this in mind. I mean, I guess one thing to do is to if you have your fancy filter is to filter either and just measure, yeah, I guess lifetime as Milo suggested, or G2 maybe, I don't know.
All right.
What's the figure on the bottom right?
So yeah, there's quite a lot going on this page. We could talk about phonons, but I guess the main idea is that we don't want the phonon assisted recombination photons. We want the zero phonon line photons. And these ones are phonon assisted and these ones are not. So that's the main idea. We can come back to this if you really want to.
well, Jake, actually, do you have the paper there?
Which one?
There one. Actually, interference one, like that spectrum is quite different.
This is
This is that. It's quite different, right?
different.
It's kind of weird that when they zoom in, they don't see the little hump, which they do see on the main plot.
Yeah, but they do mention in their first paper, they mentioned they have low energy acoustic phonon mode and then these higher ones, which map onto what I see this one. The other thing I wanted to demonstrate here is that this is from that first paper, their high grading PL spectra that they did, and this is the one that they used for this current paper that they did two-photon inference in. So you can see that the scale here is in 0.5 nanometers, and these ones are quite fat relative to this one. So they say they use the same emitter creation method, and somehow in the beginning they were getting this, and now they have this thing which is just super narrow. So I guess it's just interesting. Yeah, I think that's what I'm getting from this is that they just got lucky, maybe, or it was a fluke. Let's go with that. All right, moving on. So we want these zero phonon line photons because we don't get that.
Hold on, wait. Why did you have the stuff about phonons on the right side? Skipping over that.
Just in case people wanted more information about the difference between the photons in this frequency than these ones, but the main point for this paper is that we don't want these ones because the dephasing introduces distinguishability, which reduces the visibility of your two-photon interference. So the idea is that we want to take this spectrum and only get the zero phonon line photons. There's a few ways to do that, including in the beginning separating between whether you excite resonantly or non-resonantly. For the resonant case, there's a bunch of methods that people have come up with to discriminate between the excitation, laser, light, and your emission, which have the same wavelength. So what do you do there? This is a method called cross-polarization, where you send your laser in with a certain polarization. It excites the emitter, you get laser and fluorescence back, and then the polarizing beam splitter here ideally gets rid of your laser and only lets through your SPE, your quantum emission. this is what you kind of see on the output, and the idea is that all this is kind of laser here, and you want your emitter fluorescence to be sort of occupying this region in the middle. Another way to do it is to use waveguides, which we've talked about a few times. You have your excitation from one direction and your collection from a different direction, such that you can block out your excitation laser source, ideally. This is a really interesting method called dichroic excitation. There's a few papers come out about this recently. The idea is that you have some frequency corresponding to the energy difference between your two-level system, and instead of having a laser that is exciting exactly on resonant with that frequency, you use this creative two wavelength excitation scheme, such that these wavelengths are different from this one, different enough that you can place some kind of filter in your collection and get rid of them. Nevertheless, they sort of combine to excite your emission, your emitter, and the kind of the way that the dynamics of it is, it kind of looks like this. And there's some interesting block sphere equivalent pictures, but I won't go into that. And then there's another version where you have pulse excitation, and instead of collecting everything that you get from this pulse, you just try and open the gate for collection as late as you can, so that you're not collecting much of the laser, but you're still capturing the fluorescence from the emitter. And the idea here is that the emitter has a much longer lifetime than the duration of your pulse. Also pretty tricky. So all these ones are difficult, but there's things you get using resonant that you don't get with non-resonant. Nevertheless, the way that they did it was non-resonantly. So they just excited with a high energy laser, and then filtered out that excitation, and also filtered the spectrum to get rid of these ones. So they kind of combined two things here. They initially found an emitter that was naturally narrow anyway, and from this plot, there's minimal, negligible spectral diffusion, and it's very narrow. And then they used a transmission grating, which employs diffraction to further filter the spectrum, and that got them something like 100 gigahertz of the spectrum that they could collect. Anyone want to comment on the trade-offs between these two methods? I hadn't really thought about it. Yeah.
May I ask you a question that's sort of aligned to your question? So Dirk, I think in that PRL on the tin vacancy with the diamond waveguide, so I think that's analogous to the top right, measures about 40 dB of laser at the collection. How does that compare to these other techniques?
Yeah, it's a good question.
Maybe the cross pole is the easiest one to answer. So you get way more than 40 orders of magnitude.
40 orders of magnitude.
No. Orders of magnitude higher laser.
Yeah, that's something I definitely want to get more savvy on, is to be able to quantify the difference between these approaches. And I don't know that off the top of my head.
My gut instinct, if it's a 2-photon interference, that the laser powers can be crazy high, and so your decoherence from maybe a bit greater than that stuff. But someone's intuition doesn't work with lasers, so probably ignore that.
Yeah, I'll think about that some more. Does anyone have any comments on that at this point?
I didn't hear what John asked,
I
Jake.
guess the question is, if you wanted to employ resonant excitation and you had at hand all of these methods, which one offers the best opportunity to get rid of your laser and only let through your fluorescence?
Very well paraphrased.
Type collection is the one that they use in quantum dots, that you can effectively get rid of most of the lasers, but in all of them you have a bit of laser.
Okay, so Moran, reckons Moran would vote for side collection, but in all of these, there's always some non-zero.
Yeah, site collection, top excitation, or vice versa is always the best.
I think there's a nuance to point out here with side collection. Quantum dots, it's very different because it's sort of the quantum dots have Bragg reflectors above and below them in their like design. That's part of the growth process. So there's this bulk gap between like layers of like fabric pro mirrors that make it much easier to excite quantum dots in plane. Whereas if you have a waveguide and you're coupling to a waveguide, it's slightly different problem, which we often gloss over. So there is a difference between like quantum dots and like 2D materials coupled to waveguides.
Yeah, they're all very system specific, aren't they? It's not like the technique which dictates. It's kind of the system, like the bottom left, that's going to be your super long lifetime, isn't it? So we rule out a lot of spots that it's just.
Well, like in crossbow, I don't think that you can ever get rid of laser.
Yeah,
If you need super flat surface that doesn't change your laser in the friction, which I guess it's very difficult to have, right? You just need small amount of scattering that you always have. So in off resonant filters can be efficient, more efficient. And can do this sort of comparison, but yeah, can't just so okay, this is the best system specific.
But the up resonant, that's for up resonant, you have to have broadening the light.
Broadening line width for what?
Yeah,
Off resonant?
yeah, right.
Yes, you do.
So yeah, play off there, so and it's
Yeah. Best you would get resonant excitation this size visibility.
And by the way, for the quantum dots, I think that they copy from the people from the cavity 3D people. They always have some side excitation, and then they collect on the horizontal. So the excitation collection is 90.
Yeah, it's like inherent to the system.
The cavity 3D.
Yeah.
And the cavity here, they excite on here, and then they collect on the differentiation.
All right.
Always.
So now, finally,
But Greg, did you have a simple answer to your question, or was it just
With-
this system specific discussion?
what was
Like,
the
like it depends on, surface roughness, like for crossbow, so on, like for trade-offs.
oh yeah, so
But there's no perfect answer here, right?
one question is which of these is the best, and I guess we've decided that it depends on what your system is and what your capabilities are and what you're willing to attempt. And then another question is what do you get from resonant that you don't get from non-resonant, and vice versa. And
Yeah, well, that's a more fundamental question, right? There's a very precise answer there.
For sure, that should be do in resonance. Sure. But
Well, I guess you can do off resonant as long as you can filter your lines.
yeah, but your visibility net. I mean that your visibility never go to unity.
Well, get very close. I guess the previous slide that you showed was single molecules, right? They
That's
had this
important.
immune, whatever gas filter. The visibility is like 99% or something. Go back. This one.
This different paper.
The optical. This is single molecule of resonant excitation. They just filter.
Oh, right, yeah.
99%. Well,
Yeah.
of course, if you want resonant, you probably get 99, but it's very close.
yeah, I was going to say I would expect resonance to be higher, but I guess yeah, this is already pretty high for non-resonant.
I mean,
So-
you can filter narrow, it just lose a lot of photons.
What is the grid? The grid is
Let's say electron interference.
Green and red, what is it?
The parallel.
How can they get 94%, then you have the 0.5 for the cos and 0.3 for the parallel.
Plug these two numbers into this equation, you get this number.
Well, we can use that paper and.
This minus this divided by this. You get this number.
Because normally there should be the equation should be the difference and the sum. They just take the difference and divide for 1 meter. But
Well, I guess yes, that one is very close.
so normally if you have a flat line and then very deep here, then basically one. But here they have the 1/2 deep and near 0 deep. But they climb, but they have the visible near 1, and I talk about it.
Yeah, it's this is the equation they're using.
Yeah, but
Do you disagree with this equation? Or do you have a different method?
I don't mean that the visibility, how if you have the flat line for your possible. So the visibility now,
You don't get flat for
that's what we want. We have
No, your point, like ideally 1.5, 0 and 0.5.
Yeah.
But in papers, you see numbers above that one because you always have background laser leakage, so it look like normal like G2. So they just look at the difference there and quote the number. Some fine papers that they talk about like 0.5 and 0.7 stuff like that. And they measure it. But ideal, yeah, because Jake shows the theoretical values, 0 and 0.5.
So this is the main figure from the paper, and the top is just a setup. So all of this should be familiar, or at least intuitive. They're exciting with a pulse laser source, and they're using this basic setup to direct the fluorescence into this interferometer. So the main filtering, because they're doing it off resonantly, they're filtering the ZPL using this grating here, and they send it into the interferometer, and they can switch. So firstly, this delay line here has a length determined by the pulse repetition rate. And then secondly, this liquid crystal retarder, which I don't know exactly what that is, but what it does is it just changes it allows you to set the polarization. So this is the thing that they use to go from being parallel polarization to perpendicular polarization. And that's the way that you can then get your visibility. So the two key aspects of this setup are this filter here, which gives us or gives them the very narrow bandwidth from which they can extract their ZPL photons, and then also this polarization setting thing here, and then you just have this standard APD setup. Does anyone have any comments on the experimental setup?
Horrendous schematic, that's a nightmare. And why don't they use the standard like halfway plate or like what's this LCR? There's just less loss.
I'm not sure what the pros and cons are there. I've never heard of liquid crystal retarder, so
This was your original design for this measurement. It's with a continuous wave laser, or you still want to do both?
I think we had, I can't remember exactly what our short list of ones were.
Fair enough.
We looked at like free space and fiber based, and some of the issues were getting beam splitters that were optimized for this wavelength, fiber based beam splitters, that is. So I don't know exactly what they used here, or whether that was something that we did figure out. Or yeah, I can't remember.
How long is that delay on that? Say curiosity.
It's a good question.
3.7 meters. I think the LCR has the ability to change polarization arbitrarily. So, say the delay line induces some retardance, which isn't well compensated with just a half wave plate, with just a water plate. I think you can in LCR to create any arbitrary polarization. I don't know if that's what they do, but
That's the
maybe
same
that's
with your those 4 pedals, like 3 pedals.
Yeah.
You have combination of pulp phase, so I guess it doesn't really matter, like paper just use pedals, some people use free space. Just changing the polarization.
So C is the G2, just from the emitter, and
Yep.
then D is the HON.
Yes.
So we're looking at the difference between blue and orange there.
Yeah. This is the main result, and you could even just look at this single column here is the main result with data. The blue is the distinguishable case, so they've set this polarizing element to have the perpendicular polarizations at the beam splitter, and you get something that sort of, you get this bunching above 0.5, analogous to this kind of setup. And then the orange is when they've set this in the parallel polarization, and you get the dip below. Then your visibility is this difference divided by this height. They do some interesting post sort of analysis considering the purity in the regular D2. They then use that to get this kind of corrected visibility. So this is the raw visibility that you get from the ratio of these two values. And then they use the purity here to bump it up a little bit. I'm not really sure how this works. Does anyone have thoughts on this? Take the regular single photon second order correlation purity in this function, and that gives you a corrected one.
I guess they somehow get into account how much data leakage they have, difference that we have. They do also this analysis, say, okay, this you're far from like that one visibility of one, and then that part of it, like the T2 star, and part is laser, and part
Right.
sure what exactly they from various measurement they just calculate this amount, and then they still pay this 44% visibility that we see here is reduced from one because of this portion of this event.
Do you have any comments on like C here? You've got now it's also D. You've got like error bars above each of these sort of columns. And I suspect the error bars come somewhere from the shot noise, given the new count rate that they've got on the detectors. But it looks to me like the error in like the realized coincidences is larger than the error that they expected from the shot noise. Do you have any idea, like, if it's reasonable to continue using uncertainty from these smaller error bars when it's clearly the case that the uncertainty in their measurement is larger than what they're accounting for?
I've not thought about that. It's interesting. What would you say?
I don't think it's reasonable, but I've never really thought about it in G2. We always have this uncertainty in our coincidences on the x-axis, and like Swabian conveniently spits out, the shot noise uncertainty, and only sometimes does your fit, fall within the bounds of the uncertainty that shot noise comes out as. Sure. The other thing, the classical limit here is 1. That's, that is good.
So what was the comment here?
Shot noise isn't just from the place, like
No, not going to later through count rates. I didn't say that.
works.
Oh, no. It should integrate the count rate for the number of photons detected per beam for some given time. which will be dependent on your instantaneous count rate over the entire collection. At least that's my understanding.
Can I ask a question about HOM value?
Yep.
Is it kind of like I guess with a G2, you know, like, you know, that the cutoff is like 0.5. If it's below that, you know, you got a single. Is it kind of like I know you said in the perfect case, the value will be 1 when you've got, you know, no sort of interference, it'll be 0. But is there like a kind of threshold, or it's just like the higher the better? Is it kind of a number that people shoot for? Does that make sense?
For the visibility or the
Oh, sorry, yeah,
the value
visibility.
that exists?
Yeah, the visibility, yeah.
In the
maximum, right?
yeah, so the parameter visibility ranges from 0 to 1, and in the case where your value at where's my mouse? The value at 0, if that goes to 0 for your parallel polarization setting, just thinking out loud here, I think it doesn't matter what it almost doesn't matter what your perpendicular value is, because in this equation, this is 0, and then this is the same, so you get visibility 1. But then obviously you want this to be as close to 0.5 as possible, which would reflect, in a sense, your 2-photon purity.
Yeah.
Instead of 1-photon purity, your photon state number purity. Yeah, so I think the same thing, that the same sort of arguments that lead us to account for in the regular G2 differences between 0 and whatever the dip is below 0.5. The same sort of heuristics are employed in the HOM to explain the difference between the perfect case and the observed case.
I guess it's just like, so say you guys did this experiment, or I just say anyone does this experiment, but they get like that visibility of like, you know, 0.1 or something very low. Does it still, like in that case, can you still say, hey, look, this is clearly 2-photon interference, or is it like, that's what I mean, is it like sort of cut off where you're like, look, this is probably not legitimate, or does that sort of make sense, or it doesn't really matter? It's like they've pretty sure.
So Angus, I guess if you see any difference between the horizontal and the vertical, even a tiny bit of difference, you're good to go. So of course, it's pretty much useless if the visibility is below 95-97%, because I mean, if you all watch the videos, what this visibility gives you is the probability of entanglement, and if your visibility is below 0.9, you have no chance to entangle anything. So yeah.
Okay, that's cool. No, that's I'm just sort of curious, like whether it was, yeah.
So there is no like hardcore metric, but there is like, you report anything if you see any difference at all.
Yep.
Most of it is useless, but for actual usefulness, you really need high indistinguishability.
Okay, cool. No, that's good. That's good. That's added some stuff. So that's really good. Thanks.
That's a good point. Thank you. Okay, so this is the main result, and then they add another few paragraphs talking about what happens when you vary the time that you sort of collect the emission, and what that does to the visibility. So
Jake, this part I did not actually understand at all. So if your emission, if your spontaneous emission lifetime is, let's say in this case 1 nanosecond, right, or 2 nanoseconds, then what's the point even looking above that?
what's the point in what?
In looking above that time.
Let's start by explaining to people what this is.
What's the point in collecting more than the lifetime?
More than the spontaneous emission, yes.
Well, I guess the in a sense, the longer you're collecting absence of any other effect, the less you need to do the whole experiment for. They did this for 36 hours. But the trade-off there is that you get increased purity phasing, which reduces your visibility, as I show here. So even though the lifetime is, you do an experiment, you do a lifetime measurement, you get something like this, and your lifetime is the time at which the decay reaches half of the max, I think is the definition. But obviously, after multiples of the lifetime, you're still getting, in a sense, you have a non-zero probability of receiving photons after that. So I guess that's why it makes sense to collect for multiples of the lifetime.
I'm not sure I actually get it or understand it, to be honest.
I definitely didn't understand this bit, how they get from here to whatever this is, and then from there to an estimate of the pure phasing rate. Does anyone have any input to that?
So I guess the way you can imagine this is that you do this HRM experiment, you have a filter, because if you take that Fourier transform, it's going to be your spectrum range. So if you have a filter that you can start narrowing it down, you're basically looking at the effect of that on your visibility. And of course, when you get it narrower and narrower, because you are going to filter out those dephasing rate more and more, you start having more coherence photon, and as a result, your HRM dips increase. And as you start opening your filter, basically, you start having more decoherent photon, dephased photon in your system, and you degrade basically. So instead of doing that with a physical filter on your spectrum range, here we can just do post-processing by basically time gating your photons there. That's my understanding. That does make sense.
Yes.
No.
Right. So I ask a question. Anyway, so how does this plot on visibility as a function of this detection window width? And like, it would make sense to me. Actually, well, maybe the question is explicitly like, do they move this delta t in time, or do they just change the width and keep it centered at the same position, or do they move it with respect to? Do they shorten it with respect to 0, so it gets closer to 0, or it gets closer to 3.5, like the figure above?
It's a pulse of laser,
Yeah,
your
the
0
expand
and
it
then
without.
time extend from there.
From 0.
I don't think it starts extending they're extending the duration.
It's not.
It's delta T.
I think it's unclear what they do.
To extend
I agree that it makes sense.
So ego, does it make sense or not?
No, to me it doesn't. But I mean, if they do it, it must be working. So.
What about my explanation?
Yeah, what you said.
Makes sense.
Just
I guess it's easier to imagine that
how
way.
much of the envelope are you looking at for your opposite? If you're looking at the whole envelope
Yeah.
and there's no purity phasing, OMDIP should change, it should stay at 1 for the entire thing. But instead, they find that actually, if you look at like a smaller section of the envelope, the visibility goes up.
So I actually think that it's useless, because if they would optimize their collection efficiency, I think the whole thing is just because of their very low probabilities. I think if you increase your probability to detect a photon, this envelope is not going to give you much, because the reality is that only the photons that emitted within the lifetime would contribute to your interference. So I think what they do is they're trying to collect this multiple, like they're trying to collect these consecutive photons, presumably within this extra emission times, because their overall connection is very, very low. the overall collection efficiency. Like go to the web, go back to their schematic, right? So I reckon their collection efficiency is probably under 1% by a long shot, right? So they basically have no photons in the system. That's why they need to collect for 40 hours, and to increase their probability to get photons in the system, they vary this gated collection. But I think if you operate under a better collection efficiency, so that's where, like we're trying to do with waveguides or with the bullseyes or with whatever works, then you don't have this problem at all. You don't need it basically.
Yeah, so the just changing the collection timing is kind of, it's almost like a non-invasive way to attempt to increase the visibility. So I think it's a good point that you made that there's lots of ways to increase visibility that including using losses in the system.
Yeah, I really, and that's why I think that's why, like the quantum dots people, that's why their data now is quite good overall, because they're only using these dots in pillars, which gives you this high collection, so they have enough photons in their system. So I don't know if Helen or Leslie are here, but we're waiting for bullseyes, and Milad, we're waiting for cavities and waveguides. Now it's really important. If this system is actually as good as these guys suggest, then with a simple cavity, as I think they also wrote it in the conclusion, or a simple waveguide, your visibility would basically improve by a factor of 10 at least, and your collection time would be reduced by a lot.
Is Jake? I suppose I'm missing the point here. You know, overcomplicating things. I feel they're missing the point. The longer the collection window, the more likely it is that fewer dephasing will be here, right? Yeah. Like the larger the chance that you'll have an interaction with the quantum, hence your visibility will go down because you're phase shift. It's more likely to occur. So if you have a very small collection window, right? If you on average, if you interact like completely unrelated to the excited state lifetime, like when you're in the excited state lifetime and excited state, the electron is in the excited state, right? If your collection window is, let's say 20 nanoseconds, it means that this is when you're collecting even those photons which are emitted out and being there for 20 nanoseconds. If you're there for 20 nanoseconds as opposed to 1 nanosecond, your chance of interacting with the quantum is much higher, right? Because there is some quantum interaction rate that's separate from the excited state lifetime. So the longer the collection window, the longer the visibility will be, because the larger the fraction of the photons that make up your measurement that will have interacted with the quantum.
But
isn't that as simple as that?
Yeah, that's exactly what this measurement is doing. And it's saying if you map this to a curve, then you can extract the rates of basically.
now hold on, I think like Miloš, isn't it the quantum rate always like very fast when you talk about like picosecond extraction happening, right?
Well, sure, but in 1 nanosecond,
I think like
use less picoseconds than
it shows that the spectral diffusion actually is like playing a part. I don't think like, because like those interactions happen in
actually,
picoseconds, so you're
no, I guess it's all contributions, including spectral diffusion.
so this was showing actually the spectral diffusion is not that fast, like in
okay, but the same principle, right? Like, so dephasing through all mechanisms.
but I don't think like with the opponents we can do it that way. So if you already had like a lot of opponent contribution,
You don't think it will make much difference?
yeah, I think the reason that they see like 0.8, that's basically your opponent contribution there, maybe. That's basically your limited.
Yes,
So I assume this happened very fast, like in picosecond. This measurement. But again,
with your answer, that's not quite following your answer. I'm sort of about that today.
the background the same. So I thought like this measurement shows that most of the effect is coming from the spectral diffusion, and that's why they said, okay, if you put it in cavity, basically increase the rate, then your visibility can even be much higher.
Do they actually attribute it to something? I mean, it clearly shows the relationship between visibility and coherence, and coherence gets worse at longer longer delta T times.
Hold on, okay, do you want to finish that? Because something you just said doesn't add up.
Well,
Yeah, I'll jump to your thing first. I think they also say that the defacing due to phonon interactions is improved in a cavity. So if you reduce the lifetime, and then your argument doesn't really hold, right? Like, because say you reduce the lifetime from 3 nanoseconds to 0.5 nanoseconds. And then if you're saying that the phonon
all this
interaction-
contribution change if it goes to the cavity.
well, that, yeah, that, you know, if you're coupled to a cavity, that you not only, you don't only get a improvement due to suppression of spectral diffusion, but also due to pure defacing. So isn't that also the case?
Well, I don't know, is it like, I start like,
I thought it
cavity
was-
doesn't change those coupling to the phonon mode, so you always have to just get lifetime reduction.
No, but I think, yeah, but that's the point, that's what I thought the point was, that because of that, like it's sort of contradicting what you were just saying, that the lifetime reduction shouldn't make a difference, right? Because the phonon interaction rate is so high. Whereas I think
Well, it should have, it affect the spectral diffusion, because in the cavity you have the
but
same
not
rate.
only phonon, well, yeah, let's
So
forget
with
spectral
phonon, I'm
diffusion.
not sure, like, I think that it doesn't
I was
affect.
under the impression that there are always these comments. in
No,
this-
Miloš, it's not only about lifetime reduction when you have a cavity, it's also about the fact that your cavity is, so all your other parameters remain basically the same, but what the cavity gives you, it gives you spectral filtering in addition to an increased photon flux. And so this together gives you presumably a better visibility.
Yeah, that's the spectral diffusion argument,
Yeah.
but isn't there also an analogous one where they claim that this pure defacing is also improved as a result of coupling to a cavity?
I don't know about
That
that.
that's
That I don't know about that. It can be, doesn't have to be, I guess.
Stay in this bit.
yeah, that's what I thought was the case, but that would seem to contradict what you were saying, right? I mean, unless there is some other mechanism, like unless it actually decreases the cross section for interacting with the phonon somehow, as opposed to just that lifetime reduction that is the dominant effect.
I mean, the other thing that like we've like raised briefly, not explicitly, is what you just alluded to is they only attribute this change, this T2 star, or this rate to like pure defacing. And they like reference a couple of papers and they say that the only cause can be pure defacing, but like you say, I'm not sure that is the case. I think spectral diffusion may also affect this, and I'm not sure it affects it in the same way. I don't know, have you thought about that?
What would you say about the sentence that in a false regime, it looks like they're claiming the better experience?
Well, I think in terms of actually I looked at both of these references and neither of them actually support this claim. And I was like, anyway, but I think if we even think about it just from like a macro scale, like if the spectral diffusion is on the order of the lifetime, then it will be an effect to keep the measure like this. If the spectral diffusion is faster than the lifetime, then you're going to get something like this. If it's much slower than the lifetime, and much slower than your delay time, then it is in this case where it is not going to be in the false regime. You're not going to see it. So it really depends on the rate, for me, what the rate of spectral diffusion is. And if it's shorter than, it's going to be particularly hard to discern the difference, because essentially what you're doing is you've got to think about it in terms of those slide 3 or 4 you had, where you had the convolution of the two wave packets, and you have this dip, and the width of that dip has some certain shape, and the shape of that dip will be the information about whether it's dephasing or spectral diffusion. And I think that will slightly change the shape of this right-hand figure from, I don't know what shape that is, but I imagine there'll be a difference between the Gaussian and the Lorentz.
The word defacing is consistently used to refer to quantum interaction, right? Separate from spectral diffusion.
Yes. I don't know where this change happened, but initially defacing was just anything that was changes in wave packet. And then after, at some point in time, it became only related to photon phasing.
Yeah, because I guess so this DRL, right, the 2022 one that Igor put up, tin vacancy, it's there as well. Crystal enhancement, blah blah blah. You know, due to coupling capabilities, increases the decay rate, and thus reduces the temperature to be phasing the geometry vacancies. I read in completely the same.
Did you read this? Did you read this?
No, this is the.
No, that's me.
Igor posted the papers.
Yes, I declined co-authorship, Simon. I declined co-authorship. It was too good.
It's a current DRL, so I'm just wondering whether, you know, what's the definition of dephasing here? Does it just refer to strictly speaking? Like I was assuming it refers to strictly speaking, these one on dephasing. And I get it.
Okay, maybe let Jake finish. Jake, is there any other thing or?
Oh, there's a few more slides.
Well, it's kind of the. Discussion.
I've come to an interpretation of this expression that this thing here is the dephasing term, the dephasing / Q dephasing term, and obviously this is the circle fusion. And this thing here is just it's the coherence term. It seems like these people say that this thing is the dephasing rate.
Total dephasing by T2.
Yeah, total dephasing.
Right.
As opposed to, or as distinct from what I would call Q dephasing, which accounts for these permanent interactions.
Right, so isn't that exactly what that paragraph says?
Well, they call it, yeah, total dephasing rate
Of an optical trench.
Spontaneous emission
It's
rate.
good thing about it, like the optical
Produced by Serviers other than vacuum.
Yeah, so I mean, it depends.
Well, no, you have to be careful with those asterisks, right? If there is gamma, then there's gamma asterisk.
Well, I guess they put all the dephasing rate into one gamma star.
It's the same as the same set with that. But I think it's annoying. It's one of those things that there's like 5 different ways to name all the elements of this expression, and it's not consistent, even among solid state platforms, let alone talking about spin phasing. Anyway, one last thing that I thought was interesting is they dropped in another reference to our prior newspaper to anchor their estimate of the pure dephasing rate. Or, I mean, again, they call it the dephasing rate. Anyway, pure dephasing rate is several nanoseconds, and they sort of talk about that as being comparable to the only other attempt to estimate that in the literature, which is from our paper where we did Bragg oscillations. And what's interesting is that they quote it's understandable. They quote the numbers from this plot on the left, which is the archived version. So it's the only one they would see. And since then, it was rejected from the first journal, and then after comments from the reviewers of the second one, I went back and obviously changed the label for one being on one axis to this, but also looking into the fit that I did this. And, I mean, the fact that they like question why this number is so high, like I don't think these numbers would make sense to me looking now. That this is more reasonable, given my limited understanding of this concept to begin with. But I think this is interesting that, like, it's going to be interesting to see what happens to this sentence as this paper goes through its review process. At the same time, this paper goes through its review process. But now it's changed from the archive version. So it's going to be interesting. Is this well? Maybe. I mean, I did this before this came out. That's true. This is my attempt to correct my results. Like, not correct, address maybe some. Yeah, so it's going to be interesting to see. Also, I thought was curious was the lifetime they measured was it's not hugely different, but this is one of the factors that kind of contributes to this expected visibility is this ratio between your image time and twice the lifetime. So obviously, if the lifetime is very, very small, then that's going to be good for your HOM visibility. So in our sets, we had sort of poor ratio. There's as close to 0.5. We want this close to 1 as possible.
Great, when you update the archive version, there'll be another reference, which is no correlation to the claim they make.
Science. Okay, so then finally they offer some comments on what to do next. Talk about the visibility possibly increasing using resonant excitation. And then they talk about putting in cavities. Other things that I thought of is to do that. So resonant using blues. Also, you do it for the new blues or the visible blues in HPN. And once we can do that, there's some other things like doing say tests. And then further down the line, if you really want to sort of retrace what's been done with other solid state platforms, we could do, for example, instead of using the same single photon emitter with this delay line, we could use 2 different emitters on the same sample. Pretty challenging, been done for diamond stuff. Or we could use 2 different samples, and I guess that's even more challenging. It's also been done for quantum dots. Does anyone else have any thoughts about what could be done next?
Your stage 2, directive origin, pass up to stage 3, where they quantum repeater.
Oh, really? Okay. Coming right up.
Or like the one in the YouTube video. I like that video. I just
The YouTube video was awesome, actually. I didn't even know they made one. That's really good.
It's the best I've seen.
Can you do repeated with 2 photons which are entangled in the same spatial mode? Same spatial.
So Jake, I mean, when are we going to see two-fold interference in the lab? That's the only measurement that our lab has not been able to perform.
Yeah, Simon said you can set it up in an afternoon, just to set up the interferometer. Yeah, I guess practically speaking, it is a good question. As we search, as me / Simon and I search for candidate to do this, what are we looking for? We're looking at things that are very narrow, especially, and we haven't seen anything that appears to be as narrow as this one. So, what are the things that we can do to fast track that? What are the things that we can do to get around it?
So like regarding your list of things, like the obvious thing we looked at there is couple and legend enhance the emitters. That's all that's done.
Oh yeah, it's added in there.
Discussion, or is did you have that there?
Oh, that's what they.
Oh, okay, so you include that as part of your next steps, what they said.
Yeah,
So not just your bullet.
What they suggest, and then what I think of.
In addition to,
Yeah, so what's the issue with cavities for this wavelength? Which is
Too hard to make. The features are so small.
it's just hard to get the idea of
Size that you work.
but Mel reference to that's just actually patient.
Is the people who are savvy with personal factors, is this
So all
definitely modest to be getting pretty good increase in utility? Let's see. I don't know what they really face. Alright, so this is a
And what's the highest per cell factor we've actually observed in this group?
So okay, Jake and I guess Simon. So for our lab, we measured per cell enhancement of about 20.
What?
Yes.
Oh, what? When? HBN?
No, HBN, Johannes's data. So HBN 1D cavity with the per cell enhancement is about 20. So you can think about it. So there is a rule of thumb. So if your cavity is about 3000, you'll get a per cell effect of about 5 to 10. So it's doable. It's definitely doable.
yeah, so
So
But it's not easy, but it's not easy for practical reasons, because it's not enough to have a cavity in the range. You need to make sure. Is Mila there in the audience, or is not there?
No,
He's not there.
Chief officer.
Chi, can you find Milad and slap him? Why is Milad not there? Anyway, the challenge is to make sure the emitter is actually tuned to the cavity when you cool down, because the refractive index will change a little bit. So you can't really characterize at room temperature and then cool down. You'll get a shift. So it's like it's almost like a witch hunt of this coupled emitters, because you need them to be coupled when you cool down. So in reality, you probably don't want the Q to be too high, so that when you cool down, the emitter is still within the cavity. Does it make sense?
yes. Yes.
Chi, do you agree?
Yeah, we also can tune the cavity modes, right?
Well, how do you tune the cavity in situ? It's a bit hard, particularly in the autocube. So you need, if you want to tune it, you probably need to deposit something on top, which makes it harder.
We'll find the hydrogen H very slowly the cavity, so every can just do the slow tuning. Goodbye.
Well, if you can, then sure.
Play to get to be seen.
I mean, okay, how should I say? Definitely, we in the lab, just what we have in our lab, we have all the prerequisites to do it now. So there is no showstoppers anymore. I would say that.
One thing though that I would say is probably different with these emitters, right? Like normally you're working with something that, sure, your hope is like 580, 600 or something, but you're never going to get them that close. Whereas these really sit in a range of like 435 to 437. And if you get a flake that works, couldn't you just pattern like a range, going from smaller to large? Like,
Yeah, that's exactly what Leslie is doing. Exactly that.
right, but then that's the thing. Like, then there's no need for tuning, because ideally any cavity would host an emitter, right? Like, if you get the right flake, any cavity should be able to like plonk an emitter right in the center. And
oh yeah, sure. Ideally, yes, you're
right?
absolutely right. It's
and
just
this setup, this system at least, is the closest thing we've got to that sort of
correct.
that point. So it seems feasible to have an array of, like, as long as we can actually fab the things at this size. Seems
Correct. Exactly right. Correct.
Well, you'll still have to do tuning, right?
Well, no, that's what he's saying, that you don't really even need tuning if you can make like 10 cavities and shift the mode by like a nanometer each time, or 2 nanometers, one will hit.
Yeah, only if all of them are working at the same time.
Well, everything is fine when you do it on paper. Easy. Shit all over.
I mean, one thing that we discussed a little bit is really to refocus kind of all of more people into the same goal. So I really want Chi, Milad, well, Chi while here, but Milad, Chi, Leslie, and Otto when he comes working on that exact goal. And likewise in the emitter fab, like Angus and Helen, all contributing to this one goal. And then you have the cryo team. So we should be able to pull it off in a year, no doubt, if we don't do stupid shit.
Maybe people already doing it.
Seeing as the wheels are about to come off, you can make structures to control the photonic density of states.
No, you cannot. Stop talking nonsense.
This is beyond Igor's wrath. Is that applicable here? Is that just a dumb idea at its heart? Could you hope to tune photon dephasing values if you were to integrate with these structures?
My immediate thoughts is would be beneficial as per that equation. You can change T2 by modulating the photonic states. And you will flow on out of the facility.
Yes, Igor, did your friend Josh do this? What's his name?
No, John, nobody can make phononic crystals. The dimensions that are ridiculously small, and even if they are, they would suppress bulk phonons, nothing to do with your photon-phonon coupling. There is one idea that Ton flagged a few years back of putting a mid-IR laser in parallel to the visible to pump the phonons, but there is no evidence that it will change your phonon-photon coupling. So there is no, it's basically irrelevant, but it's not our limiting factor yet. Our limiting factor is to actually even demonstrate any sort of visibility. So I mean, even in the diamond, people are not thinking about killing phonons because that's not the limiting parameter currently.
Yeah.
Yeah, well, yeah, the best choice is to get the visibility measurement implemented. Make the cavities. I reckon you'll still have to tune. I mean, if you have a high enough Q, in order to overlap with these lines, even how narrow they are, like you would have to get super lucky. You can't do it with that, right? You will design it for this wavelength, and it's going to be open. Each cavity will be randomly displaced.
Thought about using their electron beam generation techniques. Does that somehow correspond to the power of line width?
Yeah, I wonder.
Well, but narrow line width makes it like more challenging, right? Like, yeah, the narrow line width gives you the high Q, but then you need to overlap the CPL more precisely.
You're talking about emitters.
Yeah. The natural line width. So
Well, the emitters.
Yeah.
Yeah, well, Angus is kind of trying that here. It's like using the most least intrusive irradiation conditions and now annealing and stuff to not disrupt the lattice.
Yeah.
So, because, yeah, that's the other point I made the other day, everything we've measured so far, some samples that they like wipe the shit out of. Use real science language. So,
All right, I have to go to Helen Milosh Min, if we are in the audience, we have a meeting with Diane in 10 minutes. Thanks, Jake. That was good.
Yeah, thanks everyone for coming along.
Very well done.
why do you have a yellow tree in the grass at the moment?
Harmony is your line exclusion.
Oh, okay, but that's like you said.
I reckon next week we should have that's PRL. I think the idea originally was to have 3